Let's move on to double angle identities. You can see those listed here. There are three versions of cosine. The cosine of 2 times an angle is cosine squared minus sine squared, or 1 minus 2 sine squared, or 2 cosine squared a minus 1. Just a quick look at that. If I have the cosine of a plus a, we had our sum formula earlier, so it's the cosine of a times the cosine of a minus the sine of a times the sine of a. So that's our expanded version of our sum or difference formula. So if I had this winds up being a, and a is a double angle, or cosine of 2a. So this cosine times cosine is cosine squared. Sine times sine is sine squared. So you can see where that comes from. And if we make substitutions from our other identities, for example, cosine squared being 1 minus sine squared, you can see that's where we get 1 minus 2 sine squared and so on. So we have three versions for cosine. They are interchangeable, give us the same values. Again, cosine squared minus sine squared, 1 minus 2 sine squared, or 2 cosine squared is minus 1. Obviously, we only have one for the sine. You can see listed here. Sine of 2a is simply 2 sine a cosine a, and tangent of 2a, or our double angle for tangent, 2 times the tangent of a over 1 minus tangent squared of a. So here, our number 1 says to find our values of 2 theta, given our information about theta, so sine, cosine, and tangent. Over here to the side, I think I'll go ahead and write this down. Cosine is x over r, so we know x is 3 and r is 5. We'll go ahead and make y 4, so we have a 3, 4, 5 triangle. We'll start out with the sine of 2 theta. If I expand that out from up above up here, I would have 2 times the sine of theta times the cosine of theta. Making our substitutions, the sine is 4/5 and the cosine is 3/5 from x, y, and r. Sine being y over r, or 4 over 5. Cosine being x over r, or 3 over 5. For visual effect, I'll put this over 1. And I have 2 times 4, which is 8, 8 times 3, which is 24, over 1 times 5 times 5, or 25. So the sine of 2 theta is 24/25. The cosine of 2 theta, or in mark, we have 3 choices to choose from up here. Let's just do the bottom one and do 2 cosine squared minus 1. So we have 2. Cosine is 3/5. That's going to be squared. We're going to subtract 1. Let's keep moving down here. 2, I'll square this first. You get 9/25 minus 1. 2 times 9/25 is 18/25. I'm going to rewrite 1 to be 25/25, and we get negative 7/25. So there's our cosine. It's negative 7/25. Now there's a couple of different ways to do the tangent of 2a. We can obviously apply the formula here and do the work there, but a simpler version is we've learned through our work with our identities that tangent is sine over cosine. So I'm just going to do what we have up here. I already have my sine to be 24/25. Our cosine is like a 7/25. Since I'm dividing fractions, I multiply by the reciprocal, so 24/25 times 25 over negative 7. The 25s will cancel, and our tangent is going to be negative 24/7. So I think that's an easier version than going ahead and plugging those in here and simplifying. But 6 of one, half dozen another, you can try whatever you would like. Since we already had sine over cosine and cosine, we did sine over cosine. There's a quick introduction to our identities there. So let's move on and find the values of 6 trig functions of theta if the cosine of 2 theta equals 4/5. So we're going to find all 6 trig functions here, but notice we're finding it for just theta, and this time we're given cosine 2 theta. So I'm going to put one of those definitions back up here. Cosine of 2 theta was the one we just used, 2 cosine squared theta minus 1. Well, that equals 4/5. So we'll make a substitution. 2 cosine squared theta minus 1 equals 4/5. I want to solve for the cosine of theta, not for the cosine of 2 theta like we have up here. So the first thing I'll do is add 1 to both sides. So 2 cosine squared theta. If I add 1, I get 9/5. I'll divide by 2, which is multiplying by a half. So cosine squared theta equals 9/10. And I take the square root of both sides, and the cosine of theta equals plus or minus the square root of 9 over the square root of 10, or 3 over the square root of 10. So from that, we could set up our little x, y, and r chart. I didn't bother to simplify this because I want to find x, y, and r. So x is 3 and r is 10. If I do 3 squared plus square root of 10 squared, oops, let's try that again. Got ahead of myself. 3 squared plus y squared equals square root of 10 squared. Y squared is going to equal 1, which means y equals 1. I'm going to go back here and plug this information in now that we have our x, y, and r. We're in second quadrant, so x is negative in quadrant number 2. Once we have that, we can find our 6 trig functions. We'll start with sine, cosine, and tangent. Sine being y over r, so 1 over square root of 10. I'm just going to put that in simplified version right off the bat, square root of 10 over 10. Cosine is x over r, negative 3 over square root of 10, which is negative 3 square root of 10 over 10. And tangent being y over x, or negative 1/3. And then we'll do our reciprocal functions. Cosecant of theta would be r over y, or square root of 10 over 1. Secant theta would be r over x, or negative square root of 10 over 3. And cotangent, the reciprocal of negative 1/3, is negative 3. So we worked backwards from one of our identities to go ahead and find cosine, or just the x, y, and r for just our theta. That way we can find our 6 trig functions. Number 3, we have some identities here to go ahead and simplify. Cotangent x sine 2x equals 1 plus cosine 2x. We'll go cotangent being cosine over sine times the sine of 2x, we just said earlier today, a few minutes ago, was this formula. If I multiply those, the sines are going to cancel, so I have 2 cosine squared of x. Now this is one of those rare occasions where we might go ahead and work on both sides, because I'm going to go ahead and expand out the cosine of 2x as well. And since I have a cosine squared over here, I'm going to make that 2 cosine squared x minus 1. That's our identity from our double angle for cosine. The 1 is still here, so you look, I have a 1 and a minus 1 here. They will cancel out, and 2 cosine squared x equals 2 cosine squared x. Again, a rare occasion with our double angles where we might go ahead and work on both sides. We'll go ahead and go again here, sine x plus cosine x squared. Hope we all remember, as our discussions previously, that means to go ahead and take that expression and multiply it by itself. So I'll go ahead and FOIL that, sine plus cosine times sine plus cosine, which means sine squared, plus my outer and my inner are going to be the same, so there's 2 sine x, cosine x, and then plus cosine squared x. If I were to rearrange those terms, the sine squared plus the cosine squared together should look familiar as a Pythagorean identity of 1. So right here, that equals 1. So I have 1 plus 2 sine x cosine x. And then this should also look familiar. It's a new identity today. That is our double angle for sine. So that's the sine of 2x. So we have proved our identity there as well. And we have one more here that requires a little bit of imagination. I have tangent of 8x minus tangent 8x times tangent squared of 4x equals 2 times the tangent of 4x. Going back to some of our common techniques, notice our first two terms here have a tangent of 8x in common. That would leave me with 1 minus tangent squared of 4x. Now tangent 8x is not anything that we can really work with right now, but how about if I wrote that as a tangent of 4x plus 4x? Four x plus 4x is 8x. I'm going to leave this kind of off to the side for right now. We'll come back to it in a second. The tangent of 4x plus 4x is 8x, but that's our sum formula for tangent. So I'm going to go ahead and expand it out. Tangent of 4x plus the tangent of 4x over 1 minus the tangent of 4x times the tangent of 4x. And keep in mind we're still multiplying that by the 1 minus tangent squared of 4x that we had originally when we factored it out. I'm going to slide up over here. I think I'll change color so we can see it. Tangent of 4x plus tangent of 4x is 2 times the tangent of 4x. So there's what we wanted to get to. In our denominator, 1 minus tangent 4x times tangent 4x is tangent squared of 4x. And if you recall, we're still multiplying that by 1 minus tangent squared of 4x. Now hopefully you see that those two factors cancel out and we're left with 2 times the tangent of 4x. Okay, so a couple identities there to go ahead and prove. Let's see what else we have left here. Okay, notice we have these that are already basically, I'm going to say, in expanded form. I'm going to write the cosine of 2x up here. That's our double angle. Remember, that's the cosine squared minus the sine squared. So notice I have cosine squared and sine squared to match up here. It just means that this is my x or my a, so I have the cosine of 2 times 7x or the cosine of 14x to simplify my expression as far as it'll go. Our next couple three require a little bit more imagination or a little bit more work here to get there. Sine 15, cosine 15 looks an awful lot like our double angle for sine, except sine of 2a was 2 times the sine of a times the cosine of a. So notice we have the sine times the cosine, but I don't have this 2 out here. So I'm going to start out by doing is taking that and multiplying it by 2 just so that matches up. So now I have 2 times the cosine of 15 times the sine of 15. Now I can't just randomly multiply something by 2, but this does match up with my identity up here. So to make that have an offset to be equal, I can multiply that back by a half. We can always multiply something by 1, and 1/2 times 2 is 1. So I've multiplied it by 1. I've just changed the format. But now this part here, the 2 sine 15 cosine 15 matches up as my double angle, so it's a sine of 2 times 15, noting that our A is 15. So I made that 15 right in here. Or a step further, 1/2 times the sine, I'm going to assume we all agree 2 times 15 is 30. 30 happens to come off of our unit circle, so the sine of 30 is also 1/2. So ultimately this simplifies all the way down to be 1/4. Okay, so we had a little manipulation to do to get that identity to match up, but then we went ahead and simplified and moved forward from there. Let's keep moving on here. So we have 1/4 minus 1/2 times the sine squared of 47.2. Notice that looks an awful lot like this version of our double angle for cosine. Cosine of 2a is 1 minus 2 sine squared. So I have a value minus, and then I have my angle here. So 47.1 right now is my a. I need to match these up here. So I need to make 1/4 become 1 and 1/2 become 2. So if I were to take and multiply that by 4, oops, let's try that again. take this expression and multiply it by 4, 1/4 minus 1/2 of the sine squared of 47.1. When I multiply that, 4 times 1/4 is my 1. 4 times 1/2 is 2. I have sine of 47.1 squared. But I can't just randomly multiply something by 4. I have to have that offset to make it equal 1. So I'm going to multiply it by 1/4. So I have 1/4 out here. And if I simplify one more step, the whole reason we made this manipulation was because we would say it was the cosine of 2a. So I have the 1/4 times the cosine of, if I double this, I get 94.2 degrees. And one last time here, tangent of 51 over 1 minus tangent squared 51. Notice that looks a lot like our double angle for tangent, except it is 2 times the tangent of a over 1 minus tangent squared a. In other words, I need to create a 2 here, so I'm going to take this and multiply it by 2. So 2 times the tangent of 51 over 1 minus tangent squared of 51. Now 2 over 1, so I have the 2 tangent of 51 over 1 minus tangent squared 51. So now it matches up, but again, I can't just randomly multiply by 2, so I have to offset that by multiplying back by 1/2. I'm going to bring that back into play. So I have my 1/2 out here. This is the same thing as my double angle, so the tangent of 102 degrees. 51 is my A, so I've doubled that, 51 in for A. That's where my 102 degrees come from. 1/2 times the tangent of 102 degrees. And it looks like that concludes our work with